Hyen Jay Lee, and this is my lab report number 5 for Physics 2212. Let's get started. So to give a brief background of the experiment and this lab, the purpose was to observe the difference between a magnet falling through a non-ferrous tube and a magnet falling in free fall. We collected the observational data of the magnet falling through the conductive tube of aluminum foil, and we modeled the magnet-tube interaction computationally, and then we compare our computational predictions with our observed data. The fundamental principles for this lab was Faraday's law. Faraday's law basically shows that EMF is equal to negative n over delta pi over delta t, which is n where the n is the number of turns. B and A is the magnetic flux, B is equal to external magnetic field, and A is the area of the coil. To give a brief procedure of this laboratory, the procedure was we measured the aluminum tube dimensions, we dropped the bar band through the aluminum tube, and we recorded the time it took, and we repeated this process 5 times. The observation from the experiment can be seen in this slide, where the length is equal to 0.475 meters, the width is equal to 0.012 meters, the inner tube radius was approximately 0.018 meters, the total radius was around 0.03 meters, and the magnitude of mu was 1.45637. The time taken, the average time taken was 1.282. As you can see on the right, I recorded the experiment for each of the trials. From here, we can see the glow script computational model of the experiment. So the first part you see is the tube measurement. The second part is the magnetic dipole moment of the magnet. And the third part, the function, is the magnetic field function. As you can see, we initialize the variables with the observation that we found beforehand. And then we have the function to find the magnetic field. The second part, there's 4 parts in this, is the magnetic flux function, the gravitational force function, and the magnetic flux calculation. As you can see, the first part is to calculate the flux of the magnetic field, and that's found by using the radius of the ring, the distance, speed, and using the Faraday's law to calculate it. The last part is finding the magnetic field calculation, the magnetic force calculation, and the net force calculation. And finally, we can use all the findings that we did to find the velocity and position. What you see on the slide is a result of the glow script model. On the left is a visualization, and on the right is a graph that plots the velocity versus time. So from this computational simulation, we got that the time it took was approximately 1.264, and compared to our manual record of 1.282, the error rate is approximately 1.42%. The error probably results in the human mistakes we made as we were manually recording. So final questions: what if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? This would increase the induced current and make the magnet fall slower. What if holes or slots were cut into tubes? How would this affect the ring currents in your model? This would decrease the induced current and make the magnet fall faster. That is it for my Lab 5 presentation. Thanks for listening.